don't intersect the neutral axis, right? So like for this case, the 25 is running parallel to the what? To the neutral axis. It does not intersect. The distance taken is between the what? Between the applied force to the element. Okay. So I'm going to copy the same statement. Okay. And I'm going to change a bit. It does not allow me to copy. Come on. So now when the next statement that I'm going to take. So now when the distance, okay, when the perpendicular distance intersect the neutral axis, the distance is between the applied force to the neutral axis. So like for this case, it's like the 100 kilonewton. So this one I'll give you an example. So this is like the 100 kilonewton, and this is like the 25 kilonewton, right? So the 100 kilonewton, the perpendicular distance intersect the what? Neutral axis. Then the distance, this distance is between the applied force to the neutral axis, not to the element. Why? Now, if you look at element B, yeah, you got it right. But if you look at element A, you will say, hey, Eugene, that is the distance. No, okay, it stops at the what? It stops at the neutral axis. That is very important, okay? Are you all clear now? Yes or no? Do I make myself clear? Okay, so a lot of times we do get confused. Okay, even myself, I do get confused also. Which perpendicular distance to take? Is it to the neutral axis or is it to the element? So if the force, okay, the perpendicular, if the force has a distance that is parallel to the neutral axis, you measure up to the what? To the element. Okay. If the force applied, calculating the moment, the perpendicular distance intercept the neutral axis, the moment is taken between the force and the neutral axis. I want you to visualize this. Okay, this is important. Okay. Now, so once you got that concept, once you know that, so we're going to calculate a moment about in x. So I deliberately going to do clockwise, okay? Summation about moment in my x direction, okay, deliberately. So the 25 times 10 to the power 3 is going to do a clockwise rotation. Multiply by a distance of 0.5. And then plus by 100 times 10 to the power 3. Now the perpendicular distance based on the structure, the cross-sectional area of the structure designate for this problem. So it's equal to 205 times 10 to the power minus 3 divided by 2. Okay. So when you calculate this out, this will be equal to 25 plus by 100 power 3 times by 205 power minus 3 divided by 2 is equal to 22750 Newton meter. And it's going in this direction. So what you realize about here now, the thing about normal stress or stresses induced by bending is this. Okay, so if you were to recap, so if this is my normal stress, okay, so this is my normal stress in the z direction, right? So that's my stress direction in the z direction. So what we see over here is we have our intersecting point like this, right? So this is mx, so this would be our y distance. So we realize that on the other end is going to be tensile, and then it's going to be compression. Okay, sorry, I got my arrows opposite. Compression. So what we realize about this now, okay, if you look at where element A is, right? So we know that now it's our analysis time. So element A, all right, element A is going to be in tensile, and element B seems to be at where? Anyone? What is going to be the normal stress for element B for this case about moment in the x direction? Anyone? No? Come on. Anyone sleeping? So if you look at element B, it's directly located at where? At the neutral axis. And at the neutral axis is which is this position over here. That is our neutral axis. The stresses is going to be equal to what? 0. Okay, so for element B, this will be equal to what? 0. Okay, that's going to be 0. So that is how we analyze our problem over here. Okay, so the next thing that we look at, we're not done yet. Okay, so this is just one of it. Okay, so this is just a moment in the x direction. Okay, this is our moment in the x direction. So what I'll do is I'll bring this down a bit so you will not be confused. Yeah, bring this whole thing down a bit. Why confused? Because I don't want you to get confused with what is written on top. Right. So we have moment x. Then again, we are not done yet. So we have our moment P, the 100 kilonewton generate axial loading. Do we have it? Yeah. Right. Initially we defined it already. We have done it already. And then the 25 kilonewton is going to generate a shearing stress. Okay, the 25 kilonewton. So we look at V in the y direction. Okay, so V in the y direction. So I'm going to write over here to save space, or not to. I'm going to divide the page up a bit. So the V in the y direction is going to be 25 times 10 to the power of 3 Newton. Okay, and then when the V at the y, so V at the y, element A is going to be equal to what? 0. Yes or no? Because it is the outer surface. So the shear, so over here, element A, the shear will be equal to 0, right? Because it's the furthest distance away from the neutral axis based on this distribution over here that we see. And then element B, the shear will not be equal to 0. In fact, it will be at its what? In fact, it will be at its maximum. Okay. So is there anything else to analyze? So we have done our 25 kilonewton, right? So the 25 kilonewton is going to induce a moment and a shear. We have done it already. And then we have the 8 kilonewton twice over here is going to have a moment and a shear. We've done it. It's not going to reduce any torsion. And the 800 kilonewton is going to also induce an axial load and a shear. So everything looks fine. Okay. Right. So now we are ready to calculate our normal stress. So next thing we do, we're going to analyze our normal stress first. Okay. So we are going to focus now on element A. Okay. So we're going to focus on element A. So now we're going to focus on element A. So analysis on element A. Okay, we're going to do our analysis on element A. Then I'm going to take a cross-section view. Okay, I'm going to take this diagram. I'm going to highlight where element A is. So this is our position of our element A. So this is our cross-section. So this over here, right? Over here. This is our element A. Okay, our element A. So I will see if I can split the view so you can see the two values better. I wonder this will work. Give me a bit of time, okay? I wonder will this work. Okay, so what I'm going to do, I want you all to see my screen. Okay, I'm going to stop sharing for a bit. Okay, so don't worry, I will share again. I will share my desktop now. Okay, so don't worry. So yeah, you guys are now looking at my desktop now. Okay, yes you are. So now I'm going to view I'm going to have two of this going. Okay, so one of it we are looking at number one. Okay, so is this that we are looking at now? Okay, so based on the stresses that we have calculated, so we analyzed our, so on the right hand side is our stresses. So the formula that we're going to do now, okay, the formula that we're going to apply is we are going to calculate the stress Z. Okay, so we're going to calculate the normal stress. So this is normal stress, and we're going to calculate normal stress first. Oh, sorry. So our normal stress at element A. So we know that our stresses that we are going to calculate is stress Z at element A is equal to PZ divided by area plus by mx over Ixx multiplied by y plus by my over Iyy multiplied by z. Okay, so we look at our px and we know that, so if you look at the right column, okay, on the right image, are all that we have analyzed earlier. Okay, so we are looking at PZ now. So on PZ, if we look at PZ, we realize that PZ is going to induce what? Compression on element A, right? We've written down here that we're going to see compression. Okay, on element A, we're going to see compression. So down here immediately, like, so you know that this is minus 100 times 10 to the power 3. Okay. That's why it's important to write all these down in your analysis. And then once you start writing up, okay, you know that you're under compression. Or not, you stand out there, 100 kilonewton, tensile or compression, I don't know. Okay, so this is good practice. Okay, I'm not saying that everyone has to do it, but this is what I found throughout my engineering days that makes me make less mistake than before. If I don't do this, I get completely lost. Okay, it's how you manage the data. The thing about this is a complex problem. It's not easy, by the way. I'll let you know. It's not easy because you have a lot of data to manage. So organizing is going to be really, really critical. Okay. So then we look at the area. So we have a table. I'm trying to move my table. So the area that we get given here is 5320. So this will be equal to 5320 times 10. So this is in meter squared. You have to change it to meters times 10 to the power minus 6. Okay. Then the next one, we have to look at your mx now. Okay. So you look at your moment about x. So moment about x element is going to be what? Tensile. Okay. So plus of element A. So moment will be equal to 22750. Okay. 22750. Then divide by IXX. So you look at the value, what is your IXX? So over here, your IXX is equal to, so this is your IXX, 40.8 times 10 to the power of what? Minus 6, because that is plus 6, you change to meter. Now, a lot of times, again, the same thing, same issue that we all face is what is our y distance?